Section: Introduction. In this section, we discuss how deep learning has significantly impacted various fields, including natural language processing and computer vision. We focus on a phenomenon called grokking, which we define as an unexpected ability to generalize after a period of overfitting. While grokking has mainly been observed in simpler tasks, recent studies indicate it may also occur in more complex scenarios involving vision and language. We note that previous research has linked grokking to regularization techniques, such as weight decay, which seem to play a crucial role in enabling delayed generalization. For example, it has been suggested that weight norms should fall within a specific range for effective generalization. However, some recent studies argue that regularization might not be necessary for grokking, especially in shallow networks using mean-squared error loss. These studies connect grokking to a shift from lazy training to feature learning. Despite these insights, we recognize that several questions about grokking remain unanswered, such as why certain tasks lead to lazy training and the role of weight decay in deeper models or when using cross-entropy loss. To address these gaps, we propose a new explanation for grokking, which we illustrate in our figures. We demonstrate that without regularization, grokking is hindered by what we call Softmax Collapse, which leads to errors that halt learning and result in overfitting. We argue that this collapse is driven by naive loss minimization, where the gradient aligns with a direction that scales the logits uniformly. Although this scaling does not alter predictions, it can lower the cross-entropy loss for a model that has achieved perfect training accuracy, ultimately causing numerical issues. Our findings clarify several aspects of grokking, including the delayed generalization, the absence of grokking without regularization, and the effectiveness of existing methods to induce grokking. To support our hypothesis that Softmax Collapse prevents grokking without regularization, we introduce a more stable version of the softmax function. This adjustment allows models to transition from overfitting to grokking in scenarios where it typically does not occur without regularization. We also validate that naive loss minimization contributes to the delay in generalization and leads to softmax collapse by introducing a new optimizer that retains only the part of the gradient orthogonal to the naive loss minimization direction. This approach enables quicker generalization without the initial overfitting phase associated with grokking. Our main contributions include identifying that overfitting without grokking is linked to floating point errors from extreme values in the softmax function, which we term Softmax Collapse. We show that interventions to prevent this collapse can induce grokking in previously resistant settings. Additionally, we highlight how models tend towards Softmax Collapse due to overfitting and cross-entropy loss, which we refer to as naive loss minimization. Finally, we demonstrate that our new optimizer can eliminate the delay in generalization. In the following sections, we will present our findings using commonly studied grokking datasets, including results from the classic MNIST image classification dataset. Section Summary. In this section, we explore the phenomenon of grokking in deep learning, which involves unexpected generalization after overfitting, and we propose that it is influenced by issues like softmax collapse, SC, and naive loss minimization, NLM. Our findings suggest that avoiding SC through numerical stability and using a new optimizer can facilitate grokking even in the absence of regularization, addressing several unresolved questions in the literature. Section: Models. In this section, we investigate the grokking phenomenon using a two-hidden-layer multi-layer perceptron, MLP, with 200 units and a one-layer transformer featuring 4 attention heads. We train both models in a full batch setting, applying ReLU activations and cross-entropy loss, utilizing AtomW and SGD optimizers, along with our own variations, which we denote as 1 number 1 AtomW and 1 number 1 SGD. Unless stated otherwise, we set the weight decay parameter to 24 number 24. For datasets involving modular arithmetic, we concatenate inputs for the MLP, resulting in a 226-dimensional vector, while treating them as separate tokens for the transformer. We find it intriguing that grokking can occur without regularization for certain dataset sizes, but regularization becomes essential as the dataset size shrinks. Our analysis shows that when examining datasets at the threshold of these two scenarios, grokking can sometimes initiate and then abruptly halt without weight decay. We attribute this behavior to floating point errors in the number 11, which cause the gradients from many samples to become zero. We label this occurrence as softmax collapse. In modern neural networks, floating point arithmetic is commonly used for managing parameters, activations, and gradients. While it allows for efficient calculations, it also introduces numerical inaccuracies, particularly absorption errors, which we will define. We denote equality under floating point arithmetic as number 25. Absorption errors happen when two floating point numbers, with specific bases and significant bits, are added, and the result cannot be accurately represented due to a significant difference in their magnitudes. For instance, in a system with base 2 and 35 bits, adding a small number to 1 will not change the value of 1. We focus on absorption errors in the number 38 function, which is crucial in many deep learning models, especially in the softmax cross-entropy (SCE) loss. We define the SCE loss and its more stable formulation, but even the more stable version does not fully resolve the issue, as floating point errors can still arise in the summation process. The outputs of the number 11 function are constrained between 0 and 1, but the intermediate calculations involve summing exponentials of both positive and negative logits, which can vary greatly, especially with large logits where the loss nears 0. This variability can lead to absorption errors, resulting in what we term softmax collapse. Softmax collapse occurs when, for a specific sample, the logit for the correct class is much larger than those for other classes. This leads to the absorption of smaller terms, causing the SCE loss to effectively become 0. Consequently, the gradients for the correct class also become 0. While weights for incorrect classes may still receive negative updates, the absence of gradients from the correct classes is sufficient to prevent grokking. We confirm this in our appendix with an intervention that shows setting the gradients for the correct class to 0 halts generalization similarly to our observations. Section Summary. In this section, we investigate the grokking phenomenon using a multi-layer perceptron and a transformer model, highlighting the role of floating point errors, termed softmax collapse, which can cause gradients to become 0 and inhibit learning, particularly in smaller datasets. We define absorption errors and demonstrate how they lead to this collapse, ultimately affecting the model's ability to generalize. Section: Evidence of softmax collapse in grokking tasks. In this section, we explore the evidence of softmax collapse in grokking tasks. We note that grokking is often examined with smaller datasets, where we see a significant delay in generalization. In these cases, regularization appears necessary for grokking, as we do not observe improvements in test performance without it. However, we also recognize that grokking can occur without regularization if the dataset is sufficiently large. We hypothesize that as the dataset size decreases, overfitting becomes more likely, leading to softmax collapse happening sooner. To test this, we train a multi-layer perceptron without regularization on modular addition tasks, using various levels of floating point precision. We measure the fraction of samples resulting in softmax collapse at each training epoch. Our findings support our hypothesis, showing that generalization halts when softmax collapse begins, which occurs earlier with smaller datasets. This aligns with the common observation that grokking does not happen without regularization. Next, we demonstrate that preventing softmax collapse facilitates grokking. We show that methods to avoid softmax collapse lead to generalization across various grokking tasks for both multi-layer perceptrons and transformers. One method we propose is a modified version of cross-entropy loss, which avoids extreme values in logits by transforming them into probabilities in a numerically stable way. This adjustment helps mitigate the issues caused by softmax collapse, allowing grokking to occur without regularization, even as the weight norms increase. We also investigate the reasons behind the occurrence of extremely low losses and large logits in grokking tasks. We identify two main factors: the ease of overfitting in these tasks, and a training dynamic that aligns gradients with what we call naive loss minimization. Finally, we examine how the ease of overfitting in Grokking tasks contributes to Softmax Collapse. We find that larger datasets make overfitting more challenging, leading to improved performance on both training and test sets. Interestingly, we explore the opposite effect by reducing the dimensionality of input data, which makes it harder to memorize and thus prevents overfitting. Our results confirm that using lower dimensional representations in modular addition tasks allows models to generalize without regularization, emphasizing the importance of understanding training dynamics beyond just achieving high training accuracy. Section Summary. In this section, we demonstrate that Softmax Collapse (SC) can hinder generalization in Grokking tasks, particularly when dataset sizes are small, and we show that preventing SC through a modified cross-entropy loss allows for Grokking without regularization. We also identify that the ease of overfitting in Grokking tasks and the training dynamics contribute to the emergence of SC, suggesting that optimizing input representations can enhance generalization. Section: Naive Loss Minimization. In this section, we identify an important training dynamic that often occurs in Grokking tasks, which we believe is a key reason for the increase in logits and the phenomenon of sudden changes, SC. We observe that after achieving 100% training accuracy, the updates to the model's parameters are primarily driven by what we call naive loss minimization, NLM. This approach does not alter the model's decision boundary but reduces the loss by simply adjusting the scale of the predicted logits, often by modifying the model's parameters. Consequently, the logits continue to rise, eventually resulting in SC and zero gradients, which halts any further updates, including those from NLM and other beneficial components of the gradient. We formally define NLM and explore why it frequently leads to poor training outcomes in Grokking tasks. For instance, with an input-output pair of 65 number 65 leading to 66 number 66, and a predictor represented by 39 number 39 with parameters 67 number 67 producing logits 68 number 68, we define NLM as a function that reduces loss while adhering to certain conditions. We find that for a broad range of models, particularly those exhibiting positive homogeneity, the direction of the weights becomes an NLM direction when training exceeds 100% accuracy. Positive homogeneity means that a function behaves consistently when we scale its inputs and weights. In homogeneous neural networks, scaling the logits always results in a decrease in training loss beyond 100% accuracy. Many neural network architectures, like ReLU multilayer perceptrons, MLPs, and transformers without bias terms, are positively homogeneous or nearly so. Even though more complex models with skip connections and bias terms are not strictly homogeneous, they often behave similarly, especially in their last layers. We note that the alignment of gradients with the weight direction has been previously studied, showing that homogeneous networks converge under gradient descent. However, we argue that this alignment can also lead to scaling of the logits, which may cause SC and disrupt margin maximization, particularly when dealing with limited numerical precision. In practice, we see that in MLPs and transformers, the gradients align closely with the weight direction after overfitting occurs. For the later layers, the similarity between parameter updates and the NLM direction can reach as high as 0.9. Even in models with bias terms, we observe similar behaviors. To address the issues caused by NLM, we propose a new optimizer called 1-number-1-grad, which updates weights based solely on the part of the gradient that is perpendicular to the current weight direction. This method aims to prevent the scaling associated with NLM. We demonstrate that this orthogonal component of the gradient can be integrated into various optimizers, leading to improved generalization without initial overfitting. Our results indicate that the 1-number-1 SGD optimizer, a version of SGD that incorporates our orthogonal gradient approach, effectively minimizes both training and test loss without the typical overfitting phase. This suggests that weight decay may also promote Grokking by avoiding NLM. We highlight that the success of various methods to induce Grokking can be understood through this lens. Section Summary. In this section, we identify a training dynamic called naive loss minimization, NLM, which occurs after achieving 100% training accuracy and leads to increased logits and potential saturation of the gradient, ultimately hindering effective training. We propose a new optimizer, one grad, that updates weights based on the orthogonal component of the gradient to mitigate NLM, resulting in improved generalization without initial overfitting. Section: Explaining the success of existing methods for grokking. In this section, we explain the success of various methods that have been proposed to achieve grokking. Our findings indicate that these methods promote grokking by reducing nonlinear modeling issues and avoiding false positive errors associated with very low loss values. We also discuss how scaling the weights can delay generalization. While the lazy training dynamics we described play a significant role in this delay, we demonstrate that regularization is often necessary to move beyond this lazy phase. This is because scaling the weights or logits encourages a phenomenon we refer to as saturation control. In our appendix, we show that the approach used to induce grokking on the MNIST dataset with a specific loss function also leads to saturation control, which hinders further learning without weight decay. Additionally, we address numerical instability, a common challenge in deep learning, particularly with mixed precision training. We note that the exponential function is especially susceptible to numerical issues, often resulting in overflow rather than absorption errors in summation. In the context of grokking, we found that the slingshots observed can be explained by a mechanism similar to saturation control. However, this explanation does not extend to other grokking phenomena beyond the occasional spikes seen during training. We propose that these slingshots might help prevent complete saturation control, which could explain why grokking occurs without weight decay in certain situations. We elaborate on this in our appendix. We also observed problems with numerical stability when training with increasing learning rates beyond the point of overfitting.